In this second order initial value problem, y at 0 is 0, y prime at 0 is also 0. We take the Laplace transform of each term in this differential equation. Now, we covered the Laplace transform of the second derivative in the previous video. We also saw the Laplace transform of the first derivative. Let's call the Laplace transform of little y big Y of s. On the right hand side we want L of e to the minus t. Well, we can just look that up. Here it is. If we replace a with 1, we get e to the minus t, so we'll have 1 over s plus minus 1. Or sorry, 1 over s plus 1. A is equal to plus 1. The coefficient of t is minus 1, so a is plus 1. Next we insert the initial conditions. Y prime is 0 and y of 0 is 0, so these two terms go out. This term here goes out also. Factorizing out big Y of s, we'll have big Y of s times s squared plus 2s plus 2. That's what we have here. So we divide across by this quadratic to get big Y of s. Now next we get the partial fractions for this fraction here. Since the second factor in the denominator is a quadratic, it involves s squared, we want the numerator of this second fraction to be linear in s. So it has to have the form of a constant times s plus another constant. So I'll call those constants b and c. This first factor in the denominator is linear, so the numerator is just a constant, which I'll call a. Now if we add these fractions together, we have to multiply a by this denominator and bs plus c by s plus 1. So we get the numerator that way. And all of this numerator must equal 1. So let's see that. We have as squared plus 2as plus 2a. Then we have bs times s, that's bs squared. Bs times 1 is bs. Then we have c times s plus c times 1. So we can see that the s squared terms must give us 0 for this identity. All of this here must equal 1. So we see that a plus b must equal 0. The s terms must give us 0 as well. So we have 2as plus bs plus cs must give us 0. So 2a plus b plus c must equal 0. And finally the constant terms must give us 1. So the constant terms are 2a plus c. We can eliminate c between these two equations. Just subtract them. 2a minus 2a gives us 0. Then we have b plus c minus c. So we end up with b on the left hand side equals 0 minus 1. So if b is minus 1, we can sub into this top equation to see that a must be plus 1. Finally we can get c. If a is plus 1 here, we have 2 plus c equals 1, which means that c equals 1 minus 2, minus 1. So a is 1, b is minus 1, and c is minus 1. So we get minus 1s minus 1 here. And that minus sign can be taken in here. So we get minus bracket s plus 1 on top. We can take the minus sign out of these two terms and bring it here where the plus sign is. So we have minus sign here. Well, we're looking at this one here actually. Now, we've gotten the inverse transform of a function of this form before. We got it by completing the square of the denominator. See, this denominator cannot be factorized. That's why we didn't break it down over here. To complete the square, we have the coefficient of s, which is 1. We write s plus 1 and square it. Well, that's going to give us s squared plus 2s plus 1. Okay, so we get back the s squared plus 2s, we get back these terms. But we want to have a plus 2 at the end. So we have to add on a 1 here to get 1 plus 1 equals 2. Now we can get the inverse transforms. Let's look up the inverse transform of 1 over s plus 1. We've seen that a few times before. It's got the form 1 over s plus a, where a is equal to 1. So we plug 1 in here, we get e to the minus t. That one is straightforward. What about this one here? Well, this one here is actually listed in this table, but if it's not listed, you can use the shift theorem. But let's look up the listed function here. It's this one here actually, s plus a over s plus a squared plus b squared, where a is equal to 1. And you can see also that b is equal to 1. B squared is 1, so b is 1. So we're plugging 1 in for a here, so we get e to the minus t, that's this here. Then we have cos of b times t, so we have cos of 1 times t. Now if that's not listed, we can use the shift theorem as follows. This thing here has the form of big F of s plus 1, where big F of s is s over s squared plus 1. And we can look that up, something of the form s over s squared plus a squared. That's what this here is, where a is 1. So a is 1, so we get cos of 1 times t. So that's where the cos t comes from. It comes from the inverse transform of big F of s. But this is big F of s plus 1. If you just replace s with s plus 1, we get this here. And we saw from a shift theorem that the inverse transform of big F of s plus 1 is e to the minus 1t times little f of t, where little f of t is the inverse transform of big F of s. So little f of t here is cos of t. And from the shift theorem, this was called a. So a is 1. So we saw that it's e to the minus at, where a is equal to 1. But anyway, it's listed here.